Today we're going to talk about Markovnikov's rule, which a lot of people like to refer to as the rich get richer. So what I'm going to do is I'm going to make an asymmetric molecule here. I'm going to make propene. So here's my double bonded 2-carbon structure, and then I'm going to put a methyl group off the side here. So of course that means there's a hydrogen here, and hydrogen here and here. Okay, I hope you can see that. So we're going to take this away here to keep it clean. Okay, so what I'm going to do is I'm going to add hydrogen bromide to this. And the question becomes, what happens? What happens when I try to add hydrogen bromide to this? It's called a protic acid because there's a proton on an ion that likes to be negative, so it's probably going to drop a proton. Positive charge is floating around in space. It's going to be an electrophilic addition reaction, but what's it going to attack? Where is my bromine going to move? It's either going to go attack this guy, it's either going to attack this guy, or maybe it comes over and attacks this guy. We need a rule that tells us where it's going to go. So this double bond acts as a nucleophile because the electron cloud is so much more outside. If you remember a sigma bond between, I'm not even going to use an H, I'm going to use 2 X's here. Sigma bond is right between them here. But a pi bond is kind of like this hamburger bun floating above and below. So it's a lot more negative space out where it matters. And that's easy to attack protons that way because the bromine is already kind of hogging the electron. Kind of hogging it. So my proton here, hydrogen's feeling a little lonely. And what are we going to do? Well, we're going to see this electron cloud from this pi bond, and it's going to act as a nucleophile, meaning it's going to attract a nucleus, a proton. It's going to attract a positive charge. I'll tell you what, let's label carbon 1 and carbon 2 just to make sure that we are on the same page. Remember, there's 2 hydrogens attached over here. And there's 1 hydrogen attached over here, and this methyl group is hanging out. So when this pi bond breaks, I'm going to break this pi bond right now. Pa! Those electrons are going to attack this hydrogen. And hydrogen can decide if it wants to bond here, or if it wants to bond here. And the way that we discover that through Markovnikov's rule is the rich get richer. And the carbon richest in hydrogens is carbon 1. But why would hydrogen attach here as opposed to here? The reason for that is that when that pi bond breaks, one of these areas is going to bond a hydrogen. And if I bond a hydrogen here, you're going to see the carbocation appear here before the bromine is able to move in and bond. So what that means is that on the other side of the coin, if hydrogen bonds here, the carbocation appears here before bromine can move in and bond. And in that instant, even if it's a speed of light, billionth of a second moment, it happens. And the most stable configuration for a carbocation is in this secondary carbon here because it participates in pi resonance nearby like this. Look at all the space that it has because of the pi orbitals that overlap on these carbons like this. The carbon 1 doesn't have that. It only has one direction of overlap this way. So you're not going to really see the carbocation over here. You're going to see through resonance participation that the positive charge is going to be over here. And that means that this is the most attractive place for the hydrogen to be. Being a positive itself, it's just a proton, right, attaching to this area here. And then the bromine will come here as a consequence of just what's left. It's the only open seat in the room. That's what Markovnikov's rule says. And that means that this guy out on the end here is not going to be the most stable carbocation, and therefore the hydrogen is going to end up wanting to bond over here. Here's a methyl cyclohexene. Let's have a look at what would happen here if I bring something like hydrochloric acid into the mix, so HCl over here. Of course, this is a CH2, right? Because I only see 2 carbon bonds here, so there must be a hydrogen and a hydrogen on this carbon here. Yeah, you should be able to see that by now. You're a chemist at this point. And over here is 4 carbon-carbon bonds. So when this pi bond, which is kind of exposed, it's ready to attack this hydrogen here, and this pi bond breaks, and I'm going to pop it off here. Let's just remove it real quick like that. And attacks this hydrogen. Is the hydrogen going to go here or is it going to go here? Well, we know that there's 2 hydrogens here already, and Markovnikov's rule tells us that the most rich in hydrogen is going to get another hydrogen. So let's think about why. Well, of course, when I break this pi bond, the carbocation is going to end up here because this spot can participate in all kinds of delocalization of the electrons here. And it's not going to form necessarily a pi bond here or a pi bond here, but these pi orbitals are available to help balance out that positive space. So over here is where your hydrogen is going to find the most stable location for its own positive self, and as a consequence the chlorine will come off over to here, and that's going to be how we bond using Markovnikov's rule from a cyclohexene like this. Let's have some fun with this molecule. It seems innocuous enough, but let's keep something in mind here. This is a butene because there's 1, 2, 3, 4. It's a 4-carbon chain. 4 carbon chains. So that's a butene. This is carbon 1, carbon 2, carbon 3, and so forth. So this is going to be a but-2-ene, because that's where the alkene is, but-2-ene. And I think the full name for it is 2-methyl-but-2-ene. It means on the second carbon here, there's a methyl group, the first carbon, and then we have but-2-ene, like so. Okay, what are we going to do? I'm going to take an acid in water, like this. So we have a hydronium, basically, and we're going to see what happens when the pi bond attacks this proton here. The first thing we're going to note is that the pi bond breaks, and as a consequence, this hydrogen is able to bond. Now note something here. A moment ago, this only had 3 bonds because there's secretly a hydrogen coming off of it that we don't mark because we don't mark the hydrogen bonds. You're supposed to count them correctly. But look, I'll back up. Here's my double bond. Notice I'm only attached to 3 carbons at this location. So there must be another hydrogen over here, this methyl group here. I'll label them at this point just for fun. But you should be able to see that. Now let's take this pi bond and we'll attack that hydrogen with those electrons and we'll attract it over. Is it going to come here or is it going to come here? Well, let's use Markovnikov's rule. It says, to he who has everything, more shall be given. So H already over here, and consequently we know that another H is going to come here. But why? Remember from the last examples, it's because you end up with a carbocation over here, and that carbocation, that positive extra charge in the middle of the molecule, is because this is a stable spot for it to be. Look at the delocalization of the electrons here. I use the term resonance loosely. I should say delocalization. I said resonance earlier, but I don't really like that term because you think about resonance structures. But here, once we note that the carbocation wants to be here because it's in the middle of all this carbon structure where it can enjoy the delocalization of electrons and more stably sit there, we know the hydrogen, which is a positive of its own, right? It's an H+, it's just a proton, wants to be here instead. Pluses don't want to hang out with other pluses, right? Plus and minus want to hang out together. So once you see this and we know there's a carbocation spot here, we note that an hydroxyl group off of this water is going to bond here instead. This OH group, you can really think of this as an H plus and an H plus and an OH minus, if you really want to start thinking about how they've come apart, is going to love the idea of bonding to that positive group here. So that's what we really see occur. Markovnikov's rule led us to that. And this ends up as a 2-methyl-butanol instead of a butene because we've attached a hydroxyl group through the use of the Markovnikov understanding that this hydrogen will bond where there's not a carbocation, and that carbocation is located here as a consequence of this carbon's ability to delocalize its electrons along those pi orbitals there. And that is the secret to Markovnikov's rule. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.